What do you think when you hear "it's all relative"? On Merriam-Webster's website, it defines the term relative as a thing having a relation to, or connection with, or necessary dependence on another thing. Let's take a tour to understand what relativity in physics means. Nicolaus Copernicus published his work on the heliocentric theory of planetary motion in the year 1543, shortly before his death in the same year due to fear of persecution. This work argued that the Sun is at the center of the universe, not the Earth. The picture on screen now is a figure he included in his work, showing Earth, or Terra, as the third heavenly sphere from orbiting the Sun. He even included a cute picture of the Moon. A full translation of his work can be found here. But be warned, the title page reads, "Let no one untrained in geometry enter here." Before the heliocentric theory was fully worked out by Copernicus, most civilizations thought of the solar system as geocentric, which is the assumption that Earth is at the center of the universe, with the planets and Sun orbiting around it. This theory was put forth as early as the 6th century BC by Greek astronomer Anaximander. Ironically, in the same century, our boy Pythagoras posed the idea that the Earth is a sphere and suggested that it circled a central fire in the center of the known universe. This was mainly based on evidence of solar and lunar eclipses. However, the geocentric theory became popularized by Plato and his student Aristotle in the 4th century BC. Aristotle used grand depictions of crystalline spheres rotating around the Earth, each to carry a heavenly body to its corresponding position in the night sky. These spheres were said to be made of the mysterious substance ether, which is a concept that itself has an interesting history, which we will talk about in a future video. Finally, the most robust mathematical version of the geocentric theory was developed by Claudius Ptolemaeus in the 2nd century AD. This allowed for astronomers to accurately predict where a planet would be in the night sky any day of the year with reasonable certainty. Ptolemaeus tweaked the geocentric model proposed by Aristotle because at certain times of the year, planets like Mars would appear to slow down, stop, then move backward in the night sky for a period of time before reversing direction again and continuing forward. In order for the math to properly model this retrograde motion, each planet needed to have a suborbit, which became known as epicycles. With epicycles, planets did not just orbit the Earth on a circular path, but they orbited another point in a very small circle, and then that whole system orbited the Earth. Centuries later, once Copernicus worked out all the math using the Sun as the center of the solar system, the epicycles became unnecessary. As you can see on screen, Mars appears to move backward in the night sky, but that is only because Earth is orbiting the Sun more quickly. All of this is to show what relative means in physics. The accuracy of how well we can model the orbits of the planets in our solar system did not improve with Copernicus's fancy new heliocentric model. Even though we had been thinking about the solar system incorrectly for millennia, the mathematics that were developed by Ptolemaeus for the geocentric theory was just as accurate at predicting the orbit of the planets as the heliocentric theory. Most of the uncertainty in the predictions of the models came from the fact that each model assumed the planets had completely circular orbits, which we now know the orbits are elliptical. This is what is meant by relativity in physics. The place you decide to pick as your starting point or origin should not affect the answer you are looking for. The math might work out differently and be more complicated, but if done correctly, it will always lead you to the same answer. As an aside, this perfectly illustrates the necessity of both math and physics. The math may work out, but it may not be an accurate depiction of what is happening in the physical world. This is why we need to experiment and test our mathematical theory. This notion of relativity gave us a deep insight into how our physical world behaves, because it informed us that there is no special location that all measurements must be made from, and that each measurement is valid from any reference point. This shift in thinking and improvement in understanding undoubtedly played a role in the future works of Galileo and Newton. They each showed a deep understanding of this in their work by showing how the origin can be picked as anywhere given it stays consistent. In the next video, we'll talk about Newton's laws from a relativistic perspective. Thanks for watching.